Hello again, everybody, and welcome back. This is example 2.8 in our chapter 2 chapter on kinematics, and this one deals with a park ranger driving his Jeep or whatever the case may be, and he sees a deer ahead. Now, there's an interesting thing about this this problem. It's just the way that it's worded. We're told that the deer is 20 meters from the ranger's vehicle when he sees the deer, or I should say at least when the brakes are applied. Okay, but this 20 meters right here really is not a value that we can use. All it's telling is that from here to where the deer is, it's 20 meters, and we're hoping that the actual displacement of the vehicle is less than 20 meters. So we're going to just need to account for that when we write down our knowns. So this 20 meters is not really a known right here. Okay. That being said, let me take this and just kind of shrink it down and make some more room for ourselves up here. I'm going to put it right there. Okay, and so the Ranger is driving at 11.4 meters per second. So that right there is going to be our initial velocity. Okay, initial velocity equals 11.4 meters per second, and applies the brakes. And so therefore, applying the brakes, it's going to initiate a deceleration, right? Or I should say, an acceleration in the opposite direction, right? So if applying the brakes never make you go faster in the direction that you're going, right? They make you go slower in the direction you're going. So this acceleration right here, acceleration is really going to be negative 3.8 meters per second squared because it's slowing the car down. All right, so it's another thing we need to interpret, that the fact that even though the magnitude or the amount of acceleration is 3.8 meters per second squared, it's directed in the opposite direction. So hence the negative sign. I should have put in a 0 in 3.80 meters per second squared. Okay, and what's the final velocity of the Jeep? We're not really told that. Actually, we are told that right here, but we should be able to figure it out. Hopefully you bring your Jeep to a rest, so the final velocity equals 0 meters per second. All right, so part A is asking us what the acceleration is. I'm sorry, what the distance is, right? How close does the Ranger come? So whatever our displacement is for the Jeep to come to a rest, we're just going to subtract that from the 20 meters that he had to come to rest, and that'll be how close the Ranger comes. So it's just kind of worded a little bit differently, but I do want to point out that hopefully the Jeep does not displace all 20 meters right here. Otherwise, he'll come really close to hitting the deer, or he will actually contact the deer. We don't want that to happen. So displacement is what we want to find out. All right, so we've got initial velocity, we've got acceleration, and final velocity. We want displacement. The equation that we'll use is going to be the one that we usually have listed fifth. That is final velocity squared equals initial velocity squared. Initial velocity squared plus 2 times our acceleration times our displacement. Okay? Let's solve for displacement. We're going to add our initial velocity over, and then we're going to divide by 2a right here. So our displacement is going to be v final squared minus v initial squared over 2a. All right, let's go ahead and plug in final velocity squared. That's easy, that's 0, right? Initial velocity squared, that's going to be, what is it, 11.4, that value squared, right? So 0 minus 11.4, so it's going to be minus 120 something. Over what? Over 2 times our acceleration, which is negative. It's directed in the negative direction, negative 3.80 meters per second. Oh, you know what? I'm not going to do that. I usually write my units, but for the sake of simplicity, I'm going to leave them out. Okay, 3.80 end bracket, and we should have our value for the displacement. Okay, and that gives me 17.1 meters. So that's the actual displacement that the Ranger's truck undergoes. So I'm going to dotted line box that, and I usually dotted line box things when we get an answer that is important for helping us find the final answer, but it's not the actual final answer itself. So this part is actually going to be pretty easy. If it was originally 20 meters from the Ranger's vehicle, and he actually goes 17.1 meters. What is the actual distance? We might say how close? How close to the deer? Well, that's going to be 2.9 meters. All right, we just find that distance to the vehicle. All right. You know, I should have written just 2.9 because it's correct significant figures. All right, 2.9 meters, that's how close it comes. So that's about the length of a man to the deer, so that's a pretty close call. All right, part B. That was all part A, right here. Part B is how long does it take? That's all that it's saying. How much time is needed for the ranger's vehicle to come to a stop? All right, so T is what we're solving for right here. And we're going to go back, and we don't need to rewrite all of our knowns because we already have them written down. Initial velocity here, acceleration, final velocity. We should easily be able to solve for time because we know that v final equals v initial plus acceleration times time, which means that time is going to be equal to v final minus v initial all over acceleration. All right, so skidding or coming to a stop in these 17.1 meters, how long does that take? It's going to be 0 minus 11.4, all divided by negative 3.80. And again, it's a good thing that that's negative because you can't have negative time. That numerator would have given us a negative time, but since the denominator is negative, the time winds up being positive. So what is 11.4 divided by 3.80 since the negatives go away? I get 3. Big old 3. T equals 3 seconds. And that's the final answer. Okay? So that's our ranger and deer problem, example 2-8. Thanks for following along. I'll see you on the next one.